You might have seen one of these devices on a desk or somewhere in an office. They are interesting, fun devices to play with, but also holds a ton of information, including the conservation of momentum, the conservation of energy, including Newton's first and third law. Today, I will be explaining how physics is used in a Newton's cradle. So the Newton's cradle was created in 1967, and it was named in honor of Isaac Newton. So let's see, what is a Newton's cradle? So the balls are hung by a wire in a straight line all side by side. The balls are made usually of steel due to the high elasticity. The higher the elasticity, the less energy it will lose. The balls are all the same mass, size, and density to assure the energy flows through it evenly. To use this device, you raise one or as many balls as you'd like on one side, release, and watch what it does. As you can see, lifting one ball causes the ball on the opposite side to swing out. Now doing it with two balls, the two balls on the opposite end corresponded. Even lifting three balls, no matter how many you do, the same number will correspond. Let's dive further into why Newton's cradle works as it does. We see Newton's first law present in the Newton's cradle. Every object in a state of uniform motion will remain in that state of motion unless an external force acts on it. We know that gravity, air resistance, and friction all act on the balls, therefore causes them to eventually slow down. This makes the Newton's cradle not a closed system. If we had a perfect Newton's cradle where only energy, gravity, and momentum were affecting the balls and was completely structurally perfect, the balls would swing forever, therefore proving his first law to be correct. We can also see Newton's third law present. For every action in nature, there is an equal and opposite reaction. Forces always come in pairs. When one of the balls is raised and then let go, it strikes the other balls that are still in place and exerts force on them all, pushing the ball on the other end away. This then creates an equal opposite reaction. This goes hand in hand with the conservation of momentum. Momentum is the force of objects in motion. Momentum is also expressed as mass multiplied by velocity, mv. We also see the conservation of energy in the Newton's cradle. The law of conservation of energy states that energy cannot be created or destroyed. Energy can, however, change forms. When the first ball is lifted, it holds potential energy. When released, that energy turns into kinetic energy. This kinetic energy goes through all the balls, including the last one, making the last one lift. The last ball continues to have the kinetic energy until it reaches its maximum, just before gravity comes into play. Its energy goes back into potential energy. This cycle then repeats itself back and forth within the balls. Focusing more on momentum, when the first ball hits the second ball, the first ball stops moving and loses its momentum. That momentum isn't gone though. It is passed on to the second ball. That ball then proceeds to pass it on to the third ball, then the fourth, then fifth. The fifth ball then swings up with nearly the same velocity as the first ball coming down. It then comes back down and repeats the process. As you can see, no momentum and energy is being lost, but instead transferred from one ball to another. A perfect Newton's cradle would be considered an elastic collision. This would be because the kinetic energy of the objects hitting each other remains the same on both sides. Imagine if there was only two balls and one ball hit the other with an elastic collision with 7 joules of energy. The ball that was hit would also swing away 7 joules. Unfortunately, it is impossible to have a perfect Newton's cradle thanks to friction. The ball's kinetic energy turns into heat because of the friction that occurs between the ball's molecules. When the balls come into contact, they also vibrate. This releases energy into the air, which creates the clicking sound between the hits. Now, a good question may be, well, why doesn't the ball just bounce off the other balls when they collide? This is because momentum is a vector, therefore travels in a direction. The momentum can only change with the influence of an outside force. The momentum of the balls only change when the force of gravity pulls back down on the balls swinging away. This pattern continues until the balls eventually slow due to friction and air resistance. Now say if you were to pick up both balls on either end and release them, what would happen? Both ends send kinetic energy into the balls in the middle. They have no net force, so they do not move. The balls on the outside would just bounce back off, like if they hit a wall.